For our project, we chose to analyse the efficiency profile of a propeller. More specifically, get a propeller, spin it at different speeds, and measure how much thrust it produces. Propellers have numerous real-world applications, from enormous fixed-wing aircraft to small, hobby-scale quadcopters and drones. These uses require very precise control of the thrust being generated by their motors, fighting against many chaotic factors in a generally unstable system. For this reason, it's important to understand exactly how the speed of a propeller maps to the force it produces. Advanced control systems can use this relationship to more accurately steer the aircraft. Unfortunately, there is an apparent dearth of reliable formulas for such things, particularly in the hobbyist community. The most common method is to build some sort of apparatus to measure both the thrust produced and the frequency of rotation. This study will do just that, and also compare the results to a computer simulation of the same problem generated in ANSYS to prove the validity of that numerical method. We started with the real-world test. Measuring the thrust was the easy part. We built a thrust stand which pivots on an axle, transferring the force from a propeller to a weighing scale in a way that causes minimal interference with the airflow. On the other hand, measuring the frequency of the propeller proved rather more difficult.
We originally planned on using infrared brake beam sensors, which would get triggered by the blades. This plan had a few problems. First, the plastic of the propeller didn't actually block infrared light, but we solved this by applying some duct tape to the propellers. Then, we weren't getting readings out of our sensors, so we translated the datasheet out of Chinese and realized that the response time of the sensor was too low to register the blades at the rate we were spinning them. In the end, to determine the speed, we actually recorded the sound of the motor, performed a Fourier analysis. This resulted in a very clean peak at about the frequency we expected.
We suspected that since the propeller has two evenly spaced blades, that the frequency being measured was in fact double what we wanted. In order to test this hypothesis, we used a high-speed camera to observe the propeller at its slowest two speeds. The camera captured 240 frames per second. We slowed down the reporting greatly and then counted how many times the propeller spun in 60 frames. From this, we determined a frequency. Comparing the two sets of frequencies side by side proved our suspicions were correct. The frequencies measured from the sound were exactly double those measured on the high-speed video. This provided us with a baseline that validated our method. All that remained was to actually perform these measurements.
We wrote an Arduino script to turn the propeller on and off every few seconds, increasing the power each time. 135. At each time step, I would read the thrust produced and Jeff would write it down. And all the while, we had a microphone set up to record the frequency of the propeller. This actually gave a really nice time graph. Then it was just a matter of extracting the frequencies in Octave.
Now that the real-life portion of this study had been completed, it was time to simulate the same problem numerically using ANSYS. We created a large cylindrical fluid domain to represent the room of the test and surrounded it by solid walls. We set a solid CAD model of our propeller part inside the domain and set it spinning.
To create the simulation, we put the propeller in a large cylinder of air representing the room. In reality, we experimented in a rectangular room, not a cylindrical one. We chose cylindrical though for a number of reasons. First, we knew from our testing that the air beside the propeller was not affected by it, so that the side boundaries should not have much of an impact on the propeller thrust. Second, when you model a fluid flow with ANSYS, it creates finer meshes near corners, and the calculations there are more complex due to turbulence and isolated regions of air, causing simulations with rectangular boundaries to be unnecessarily complicated and slow. Another important decision we made in our simulation was to set the front and back of the domain as walls. Many tutorials that we researched use cylinders with the ends set as inlets and outlets, with fluids coming in at a normal velocity. But because our experiment was done with a stationary propeller, we wanted to set this velocity to 0. This, however, is not allowed by ANSYS and resulted in failed simulations. Our solution was to make the cylinder longer and to set the ends as walls so that they were like the walls of our room. This actually makes more sense when you think about it, since we experimented in a closed room with no air entering or exiting the system.
We solved this system all the way to steady state and analysed the result, solving for force induced on the propeller.
In ANSYS, simulating a rotating object is achieved by using a rotating frame of reference. The CFX fluid solver in ANSYS computes the Coriolis and centrifugal terms and then solves a rotating frame total energy equation, which is well suited for fluid problems. This worked well for us since it determines the thrust in the Z direction that were very close to what we observed at all frequencies. The only problem is when it comes to the visualization of the solutions. It appears as if the air around the perimeter of the cylindrical enclosure is rotating faster than the air near the propeller. This is because the air that far from the propeller is almost stationary, so in the rotating frame of reference, it appears to be moving incredibly quickly. To prove that using a rotating domain to compute propeller thrust is valid, we used the SOLIDWORKS flow simulator with the same rotational domain setup. SOLIDWORKS does domains and boundary conditions slightly differently, so according to several tutorials, the rotating domain only needed to encompass the propeller, which you can see is set to rotating. Airflow is still calculated within the open boundary, shown by the shaded cube. SOLIDWORKS allowed us to see the airflow speed in the global static frame, which produced an airflow that appeared more like what you would expect to see.
SOLIDWORKS produced some really nice simulations of the airflow through the propeller. We can see the air get sucked into a small, high-pressure region near the blades and jettisoned out into a vortex behind it.
Here's how we extract data points from our ANSYS simulation. We see in the expressions pane that the propeller rotated at 143 revolutions per second. Then we go to Calculator, select Force, and select the direction that our propeller was pointing in. We hit Calculate, and we get a force representing the thrust provided by the propeller. Going to Excel, we have the list of the frequencies we recorded for our trials, and here we have 143 Hz. Here we have the list of our thrusts from our ANSYS simulations, and here we have the same force that we just calculated.
At long last, we'd collected all of our results from both methods, and now it was time to compare them. For the physical portion, we ended up doing 2 runs of the experiment in order to minimise error. When frequency was plotted against thrust produced, the first trial showed a very nice quadratic relationship passing through the origin, which could be fitted with a trend line with an R² value of 0.999. The second set of trials produced a very similar result, this time with an even higher R² value. This similarity lends legitimacy to both the relationship between the variables and also the high precision of the experiment conducted. Adding in the ANSYS data points and trend line, you can see that once again, it produced a very similar result. Almost exactly the same relationship between the variables, just with a magnitude that was a few % higher. Since the results were so similar, this lends credence to the fact that both employed methods were perfectly valid ways of conducting this experiment. In this regard, the endeavour can be regarded as a complete success.
As seen in our results, we had a very close match between our experimental data and our simulated ANSYS data. This graph shows the relative error in our simulated and experimental data. As can be seen, the experimental data has a fairly constant 1 to 10% error below the simulated values, which meant we were averaging about 5% less thrust than the simulation. We wanted to see if this error could be explained by our experimental setup, or if there may have been an issue with the simulation. We identified one major source of error in our experiment. Here's the model we used for simulation. Notice that there is nothing supporting the propeller, but in our experimental setup, there is a pole of significant size holding it up. When the propeller spins, it pushes air backwards, and due to Newton's laws, this results in a forward force on the propeller providing thrust. With the bar in the way, however, the accelerated air hits the pole, pushing against it with a force in the direction opposite of the thrust, cancelling out any thrust obtained originally by those air particles. To get an idea of the impact of this source of error, we approximated the loss in thrust as the proportion of the area swept out of the propeller blocked by the pole. This proportion comes out to roughly 5.3%, showing that it does indeed account for most of our error.
So what is the impact of our analysis, and why should you care? Due to the similarity between the ANSYS simulation and our actual test results, we've shown that setting up a simulation the way we did and using the same assumptions will provide results that are valid. This is useful for others attempting simulations of similar propellers, since they can use a similar ANSYS setup and be reasonably confident in their results. This would also allow consumers to simulate several propellers and choose one without buying several and testing them. This is also particularly applicable to hobbyists who want to use 9-inch diameter propellers with a 4.7-inch pitch in control systems, since we've already verified the thrust versus frequency relationship that they can use. Since we determined that there was a quadratic relationship between the speed and thrust generated by the propeller, it's more efficient to have few fast-spinning propellers than many slow ones.